In this video, I'm going to go through the Edexcel AS paper from 2018. This is going to be paper 1. Just do the first half of this exam in this video, the second half in a later one. Okay, first question then. What is what is meant by covalent bond? The term covalent bond is when two atoms share a pair of electrons. That's all you need to say. Okay, draw a diagram of an ammonia molecule, clearly showing its shape, and include any lone pairs of electrons and the value of the bond angle. Okay, so I'm just going to make a bit of space here. Right, so we need to just quickly think about the dot cross diagram for an ammonia molecule, which I'll just draw here. We've got 3 covalent bonds, so we have a dot and a cross in each overlap. Nitrogen is the atom there. Nitrogen is in group 5, so it's got 5 of its own electrons. So that I've only drawn 3 dots for nitrogen, so I've got to draw 2 more, so it's got a lone pair. So nitrogen in ammonia, we can see it's got 3 bonding pairs and 1 lone pair. Now we have to think about the shape of that. Now when you have 4 bonding pairs, such as in methane, you are going to get a tetrahedral molecule like this. But of course this isn't carbon, it's nitrogen, so we haven't got a bonding pair up here. We have actually got a lone pair, and a lone pair causes greater repulsion than the than a bond pair. So instead of this angle being 109.5 as it would with methane and CH4, it's about 107.5. It's a bit smaller, and we describe that shape of the molecule to be pyramidal. Okay, so this is the diagram you need to draw. So you've got a 1 lone pair, and you've got 3 bonding pairs for the hydrogens, bond angle about 107.5. Right, now we've got a diagram there of BF3. Okay, drawing a dot cross diagram there, we can see that boron has got it's got 3 lone pairs, 3 bond pairs. Now, how can they get as far away from each other as possible? Well, it's going to form a trigonal planar structure, so it's going to be on a flat plane. As boron, we've got 3 fluorines, and the way they can get as far away from each other as possible is by having a 120 bond angle. It's trigonal planar, so the answer there is 120. There's no lone pairs on the boron, unlike the nitrogen, to cause the distortion there. Ammonia and boron trifluoride react to form a compound NH3BF3, which is a dative covalent bond. Each of the molecules has a different feature of its electronic structure that allows this to happen. Okay, now the reason why this can happen is because, of course, and I'll draw this here, nitrogen has got, the nitrogen in ammonia has got a lone pair here. Whereas if you think about the BF3, well, there's boron. And there's boron there. So we've got 3 bonds there, and boron, fluorine. Because the fluorine's in group 7, they're all going to have 6 more electrons there. I'll just draw it for 1 fluorine, not for all of them. So you can see the boron has only got 6 electrons in its outer shell. So what tends to happen is that goes there, and the boron forms a dated bond. So this pair of electrons in the lone pair of electrons in the ammonia forms a dated bond to the boron. So the nitrogen and the boron will share this pair of electrons, but it's a dated bond because both of the electrons come from the nitrogen. So I think for your 2 marks there, you need to say that the NH3, the nitrogen has a lone pair, and the BF3, that's it. It has only 6 electrons in its outer shell. It wants to have the full 8, and so it's able to accept a lone pair and form a dated bond. During this reaction change, the bond angle about the nitrogen atom and the boron atoms change. State the new bond angle. Well, what's going to happen here is when I will actually rub this out, I think. When this reacts, so the lone pair is going to form a dative to the boron. I won't bother drawing the electrons in the fluorine, but you can see that the boron now has got, it's actually got 4 bond pairs and no lone pairs. So that's going to be tetrahedral, just like methane. And now the bond angle from the boron, the fluorine, boron, fluorine bond angle is now going to be 109.5 degrees. It's not going to be 120 anymore. And the same with the similar thing with the nitrogen. You can see that the nitrogen has got 4 bond pairs. It's got no lone pairs now, and the lone pair distorts it. Okay, so that's going to be tetrahedral. And there's no lone pair to distort it, so it's going to be 109.5. The bond angle between the H, the N, and the H, rather than 107.5 when you did have a lone pair causing distortion. Okay. This question is about hydrogen. Okay. Hydrogen has 2 stable isotopes, 1H and 2H. Complete the table to show the number of subatomic particles. Okay, so 1H is going to have 1 proton, and of course the mass number up here, number 1, is protons plus neutrons, so it's got no neutrons, whereas the 2H has got 1 proton and it will have 1 neutron. Use the data in the table to explain the term isotopes. So isotopes have the same proton number. In this case, it's going to be 1 because they're both hydrogen, but they've got different neutron numbers, different numbers of neutrons. The 1H has got 0 neutrons, and the 2H has got 1 neutron. Right, now the relative atomic mass of hydrogen in the periodic table is 1.0. This is correct to 2 significant figures. So you've got a table here to show the isotopic mass and the natural abundance. Now, if you look at the isotope, interestingly, you'll see that it is not exactly 1 for 1H, even though it's only got 1 proton, because, of course, a proton, the mass of a proton is slightly different depending on which nucleus it's in. That may seem very strange, but it is. So it's not exactly 1, and the relative isotopic mass of 2H is not 2 exactly, it's slightly heavier, it's 2.014. Right. Use the data in the table to give a reason why it can be estimated that the relative atomic mass is greater than 1. Well, first of all, you're going to say most of it is 1H. Is 1H, and that weighs more than 1. It weighs more, so that alone would make it more than 1. And also, even though there's only a small proportion of that, the average value is going to be greater than 1 also, because there is some of this heavy version of the 2H present. So that will make it, it will make it even slightly higher than this value here. calculate the relative atomic mass of hydrogen from these data, given your answers to 4 decimal places. So what we're going to say AR then is equal to the abundance of the isotope, and let's put that rather than a percentage as a decimal. So it's going to be 0.999885 multiplied by the mass, the abundance multiplied by the mass, so 1.007825, and it's going to be plus the mass of the abundance of that. So the abundance of that is going to be divide that by 100, so it's going to be 0.000115 multiplied by 2.014101. Okay, and if you would put that into your calculator and you need it to 4 decimal places, right, you will get, well, if you put it in your calculator, you get 1.00794, and then a few other numbers after that. So to 4 decimal places, it's going to be 1.079. There's your answer there. Okay, write an equation to represent the first ionization energy of hydrogen. Includes state symbols. So it's the energy required to remove 1 mole of electrons from 1 mole of hydrogen atoms in the gaseous phase. So it's got to be H gas, not H2 or whatever H. It's just H, and it's going to be H plus. That's going to be gaseous, and an electron there. Okay, the sequence of the first 3 elements of the periodic table is hydrogen, helium, and lithium. Explain why the first ionization of hydrogen is less than that of helium, but greater than that of lithium. Well, we need to think about the electronic structures of these elements. Li, so hydrogen is 1s2, helium is 1s, sorry, hydrogen is 1s1, helium is 1s2, and lithium is 1s2, 2s1. Right, so let's think about why is the first ionization of hydrogen is less than that of helium, right? Well, when we remove the electron, where are we removing the electron from? In the first ionization, it comes from the 1s orbital in both cases. Okay, so the distance in the nucleus is approximately the same, right? Because it's from the same orbital, but helium's is much higher because helium, and it's a lot higher because helium has 2 protons, positive protons in the nucleus, whereas hydrogen only has 1. So that's got double the number of protons. So it makes a really big difference. H, okay. And the second point, why is lithium's lower than helium? Well, the reason why is because, so let's see, why is lithium's lower than hydrogen, strictly speaking? Okay, well, it's because in lithium, the electron is coming from where? The electron is coming from the 2s orbital, and that is shielded by the 1s. That's not happening in hydrogen because it's coming from 1s in hydrogen, and also 1s is closer to the nucleus than 2s. 2s is considerably further away from the nucleus, so 2 factors going on there. And that accounts easily for all those 4 marks there. Hydrogen can be placed in several different positions in the periodic table. One is immediately above lithium. Another is in the center of the first row. Criticize the position of hydrogen immediately above lithium. Right, so if you put hydrogen above lithium, it will mean that it's in the alkali metals groups L, I, N, A, K, and so on. That's group 1, the alkali metals. Right. Give one reason against this. Let's do against first. Well, hydrogen is not a metal. right, and then we've got to give 2 against. Okay, so 2 against, that's 1 against. Hydrogen is not a metal. Hydrogen does not form H plus ions. Now we write H plus ions, but really the H plus ion is H3O plus, is not H plus. The hydrogen will not form a single like a positive ion in the same way as Li and Na and so forth will. Okay. Another thing you could say there is that hydrogen will actually form an H minus ion. Not very often, but it does. Whereas lithium and sodium potassium certainly don't do that. So there's a few alternatives there. In favor, well, the thing we can say in favor, it has 1 electron in an s orbital. Hydrogen's got 1 in 1s, lithium in 2s, sodium in 3s, potassium 4s, and so on. Okay, so this is about titration. Sulfuric acid is being titrated against potassium hydroxide. Okay, so let's just sketch this. Potassium hydroxide was placed in a burette. It's got KOH, and we don't know the concentration. So we're going to find out. 25 centimeters cubed of sulfuric acid was placed in a conical flask here. And they add indicator, they add phenolphthalein indicator. I'll color that in purple. Actually, it won't go purple in sulfuric acid, it'll be colorless in sulfuric acid, go purple when it's alkaline. And potassium hydroxide was added from the burette until the solution just changed color. And that will go from colorless there to pink at the end point. You'll probably ask us that afterwards. Repeat titrations were carried out until concordant titers were obtained. Select the most appropriate piece of apparatus to measure 25 centimeters cubed of sulfuric acid. Well, a measuring cylinder is not accurate enough. Of course, it's got to be a pipette. Is the answer there. And there we go. A pipette. Why wouldn't we use a burette? They're pretty accurate, but they're really for delivering different volumes of liquid, and they're not actually quite as accurate as pipettes. But if you want to add one fixed volume, a pipette is the most accurate way. What is the color of the solution when neutralization has occurred? Well, it's going to go from colorless, because that's the color phenolphthalein acid, to pink. Okay, so we want pale pink when you've just added 1 drop too much. Okay, complete the table of results for titration 1 using the diagrams to find the initial burette, final burette readings. Okay, so this one here, well, that's 4.5 there, so that's going to be 4.6, and it's exactly on the lines. We call it 4.60. So the initial reading is 4.60. Now this one here, the final reading is 32.123, but it's halfway between 32.3 and 32.4, and we can read to the nearest half unit, so we call that 33.5. We wouldn't ever call it 33.3 or 4, whatever, but half unit is fine. So I put those in the wrong place there. 4.60 should go there, 32.35 there, and the titration volume, if you subtract those, you get 27.75 centimeters cubed. Right, the best value for the mean titer of this reaction. Now, mean titer, we should be looking for concordant values, and by concordant, they've got to be within 0.1 of each other, 0.1 centimeters cubed. So if we look at these values, then the only two concordant one we've got are this one here, 26.95, and 27.05. They're within 0.1 of each other. The others aren't. Okay, so if you add those together, divide by 2, you're obviously going to get there 27.00 is the average titer, mean titer. So 27.00 A is the answer we want there. Okay, calculate the concentration of the potassium hydroxide solution, giving you answers appropriate number of significant figures. Okay, so we look at the equation. The equation there tells us that you've got 2 moles of potassium hydroxide react with just 1 mole of sulfuric acid. Okay, we don't really care about the rest of that equation there. So we've got 2 moles to 1 mole is our ratio. Now we know the concentration of the sulfuric acid, so we can work out the moles of H2SO4. That's going to be the concentration times by the volume. The concentration is 0.08 moles per decimeter cubed, they tell us, and the volume, well, that was the one delivered by the pipette, 25 centimeters cubed, so that's 25 over 1,000. That gives us 2.0 times 10 to the minus 3 moles of sulfuric acid. Now we need to look at our ratio. So we need 2 moles of potassium hydroxide for every 1 mole of that. So our moles of KOH is going to be double that. So it's 2 times 10 to the minus 3 multiplied by 2, which is equal to 4 times 10 to the minus 3 moles. Now we need to work out the concentration of potassium hydroxide. So the concentration of potassium hydroxide is going to be moles over volume. This is what we've got to find out. The concentration. So the moles we just worked out is 4 times 10 to the minus 3. And the volume was the average titer. That was 27.00 centimeters cubed. So that's 27 over 1,000. And that gives us 0.1488 moles per decimeter cubed. But we need to give that to appropriate number of significant figures. Now, if you look at the data, apart from these which are given to 4 sig figs, the titers, everything else is given to 3 significant figures. Just look up here, I'll show you. This is given to 3 significant figures. That's given to 3 significant figures. This is given to 3 significant figures. So we should give our answer to that. So we need to get rid of one of those, the last figure. Our answer should be 0.149 moles per decimeter cubed. Okay, let's move on to question 4. An ionic compound contains a metal cation and a non-metal anion in a 1-to-1 ratio. Okay, so that means M, the positive ion, and N must have the same charge. So these are both +1, or they're both +2, or at a stretch +3, because they're in this ratio of just 1 M to 1 N. Right, and there's water crystallization. The compound can be represented as MnXH2O, where X is the number of moles of water crystallization. A sample of MnX was dissolved in distilled water to produce a colorless solution with a concentration of about 0.4. Okay, and the following tests were carried out. Okay, so they added barium chloride to one of the test tubes, and that gave a white precipitate. So that would tend to indicate that you've either got sulfate ions or carbonate ions present, because both barium sulfate and barium carbonate are both very insoluble. Okay, so it could be either one of those two. I've given the formula there. Oh, sorry, it should be 2 minus there. Right. Addition of 1 centimeters cubed dilute hydrochloric acid to the test tube resulted in no further change. Well, we can work out what the ion is. That means the ion cannot be the carbonate ion, because if you add acid to a carbonate ion, you get effervescence, you get fizzing, and you get CO2 released. Okay, and the precipitate will also dissolve. The precipitate doesn't dissolve, so it's not barium carbonate. The precipitate is barium sulfate, and so that means that the ion has got to be SO4 2 minus. Right, what is the charge on the cation? Well, the formula, as I said earlier on, is Mn. So that means we have got the N, and that's got a charge of 2 minus. So in order for the formula to be that 1-to-1 ratio, that must have a charge of 2 plus on it. So got to be C. Second test. A flame test gave no change in the flame color. Give a possible identity of cation M. Right, well, let's think of things which have an M2 plus charge on them. Well, you've got magnesium, all the group 2s, calcium, strontium, and barium. You've also got a load of transition metals like copper and iron and so on. But you should know that, right, calcium gives a brick red flame test, strontium gives a crimson, barium gives a green one, magnesium doesn't give any color to the flame. So the most sensible suggestion to give there, the most obvious one, I think, is magnesium 2 plus. Right, heating the compound results in the formation of the anhydrous ionic solid by the following reaction. Heating a sample of the hydrated compound reduced the mass to 8.9% of its original value. Use this information to calculate the value of X. Right, so I think what we're going to have to do here is we are going to have to presume that we do have magnesium there, so that we have got the compound must be magnesium sulfate. That would fit in because magnesium sulfate is soluble, so you can make a solution of it. Right, so to get a calculated value of X. So what we're going to do then is we're going to say that magnesium sulfate so MgSO4 dot XH2O, when you heat it up, that's a solid, is going to give you MgSO4 solid and 2 waters, which are going to, because it's hot, they're going to go off as a gas. So that's why it's got this mass is going to go down. Okay. Now they tell us that it's reduced to 48% 0.9% of its original value. So let's say if that was 100 grams, then this stuff here would weigh 48.9 grams. Okay, so what we're going to say now is if we can find out the number of moles here in 48.9 grams, that will be the same as the number of moles here. You know the moles of that, and that's going to be the moles in 100 grams. So we know the number of moles, and we know the number of grams here, so we can work out the MR, which is equal to mass divided by the number of moles. If we work out MR, then we can work out the value of XH2O there. Okay, so first of all, we need to work out the moles of the anhydrous one, this one here. Let's do that. So moles of anhydrous magnesium sulfate. And we do know the MR of that because there's no water in it, is equal to mass over MR. The mass is 48.9 grams, and the MR, so we've got 24.3 for magnesium, plus 32.1 for sulfur, plus 4 times 16 for the oxygens. That gives us 120.4. So put that in there, 120.4. Work that out, that gives us a value of 0.406 moles. So now we know this is the number of moles we've got here. So let's write down that. So moles of the hydrated in 100 grams, that's equal to this number, 0.406. So we know the MR, use this equation, is mass over the moles. The mass was 100 grams and the number of moles was 0.406. That gives us a value of 246. Okay, now how do we find out X from that? Well, we've got magnesium sulfate XH2O. Right, this whole thing is 246 grams, 246, sorry. This bit we worked out before, that was 120.4. So the XH2O is going to be 246 minus 120.4, which gives us 125.8. Now, one water molecule, it's got an MR of 18. So how many have we got there? So X is going to be equal to 125.8 divided by 18, which gives us 6.98. And so that means the water crystallization, there can only be integer values, so X has got to be equal to 7. Okay, so we have found the value of X there. Okay, that's a fairly standard thing to do. If you want to find out water crystallization, you find out the MR of the whole thing, subtract the sort of bit that you know, the rest is water, divide by 18. It's a fairly standard way of doing it. Okay, right, this question now. A student made crystals of a metal chloride, JCl2, 6H2O, by reacting the metal carbonate with hydrochloric acid. Okay, now, if it's JCl2, that means J must be a 2+ ion because chlorine is a 1- and it's JCl2. So let's just write down that equation there. So we're going to have, well, what's going to be the formula of the J carbonate? Well, carbonate is a 2- ion. So it's going to be JCO3 plus HCl is going to give us JCl2 and CO2 and H2O. And importantly, we're going to have to balance that. So that's going to be 2 hydrochloric acids per metal carbonate. So what they did here was they've got 150 centimeters cubed of hydrochloric acid of that concentration, so we can work out the moles of that. Flask was warmed and they added the metal carbonate. Now they keep adding more metal carbonate until the metal carbonate was in excess. So we are going to find out the number of moles of hydrochloric acid. That's the reagent which is limiting. The resulting mixture was filtered to get rid of the excess carbonate here. And then we will have the solution of JCl2 there. Okay. Put it in an evaporating basin. Concentrate the solution, evaporate some of the water off, let it crystallize. Don't evaporate all the water off, let it crystallize. Once the crystals were complete, filter it to get just the solid crystals and give it a little wash in ice cold water to get the final hydrated crystals, which are that there with 6 water molecules. Okay. Describe 2 observations the student might make which show that reaction in step 1 is finished. So step 1, you're adding hydrochloric acid to a little bit of metal carbonate. Okay, so I would say, obviously, how can you tell it's finished? You say the fizzing has stopped, no more carbon dioxide. And what else has stopped is, well, this was a solid and it becomes an aqueous solution. So at first you would see the solid dissolving, but the solid, they do add excess, so it wouldn't all dissolve necessarily, but you'd stop seeing the solid dissolve. No more would dissolve. That's what I would say there. What's the purpose of filtration in step 3? Oh, I think I mentioned that already. That's to get, because you've added excess carbonate, it's to get rid of this unreacted solid carbonate. That won't dissolve because the hydrochloric acid is all gone. So it's a solid, so it's easy to get rid of by filtering. Right, why do you give it a wash in a small volume of ice cold water in step 6? Okay, that would be, right, to get rid of, well, you're adding JCO3 and you're adding HCl to that, aren't you? So it's to get rid of any HCl that's left over there. That would be the point of that. And why is it ice cold? Well, if it wasn't cold, then it would dissolve too much of your, because that is soluble in water, the JCl2. And if it wasn't cold, it would dissolve it. So the fact that it's cold, its solubility is much reduced. You will lose a little bit of it, a little bit will dissolve, so your yield will go down, but you're going to minimize that by using very cold solvent. Okay, the student obtained a mass of 14.26 hydrated crystals. Assuming the percentage yield is 100%, use the information in the procedure to give a possible identity of J. Well, just to write down the equation again, we had JCl2, we had J carbonate, solid, plus it was 2HCl aqueous, went to JCl2, CO2, and water. The important thing, we've got a 1:2 ratio there. Now this was in excess, so the amount of carbonate which will dissolve is determined by the moles of hydrochloric acid we've got. So we need to work that out. So moles HCl is going to be the concentration times by the volume, and the concentration there, they told us they said it was 0.08, I think. Sorry, 0.8, beg your pardon. 0.8 moles per decimeter cubed, if you look in the earlier part of the question. I'll just scroll that up actually, just to show you. Yeah. we've got 0.8 mole per decimeter cubed, and we added 150 of that acid, okay? And that's the limiting reagent, okay? So we need to do concentration times volume there. So 0.8 multiplied by the volume, 150 over 1,000, the volume in dm cubed, and that gives us a value of 0.12 moles of HCl. Right, it's a 1 to 2 ratio, so we can say therefore the moles of carbonate reacted is going to be 0.06, and we're going to also form, well, this is important as well, we're going to form moles of JCl2 is going to be 0.06 moles. Right, now that's the moles of the JCl2 and it's in aqueous solution, and of course we're going to get the same moles of the hydrated solid. So I'm going to write down here moles of JCl2 dot 6H2O is equal to 0.06. Now we're going to find out the MR of this thing just like we did in the last question. And we're going to find out the MR because we know MR is equal to the mass divided by the moles. We know both of those. And if we can work out the MR, we can work out the identity of J by working out the atomic mass of J. So what was the mass, it said? Well, we had 14.26 grams of hydrated crystals. This is presuming 100% yield. Divided by the moles, which was 0.06. That gives us an MR of 237.7. Okay, that's the MR. Now we need to work out how much all the other things weigh. So we know here how much the waters weigh. That's going to be 6 times 18, which is equal to 6 times 18. 108 for that. The chlorines, well, they are going to be 2 times 35.5, that's equal to 71. So that means the AR of J is going to be equal to this, 237.7 minus 71 for the chlorines, minus 108 for the water, and that gives us a value of 58.7. Right, now look in your periodic table, and the nearest atom with a metal that can form 2+ ions with an AR of that is nickel, Ni. Okay, so a possible identity of J then is going to be nickel, is the element nickel. Right. Okay, now here, the student was surprised. This is a bit of a funny question. The student was surprised by the white color of the crystals because he's got nickel. Okay, this did not agree with the possible identity from J from the calculation. The student decided to perform a flame test. Explain why the student was surprised and decide why would you be surprised. Okay, nickel is a transition metal, and it would give you colored compounds. It wouldn't give you a white compound. Okay, so that tends to suggest it's a group 2 metal, you know, because well, not group 2 because they form 2+ ions and all their compounds are colored. Transition metal compounds are usually colored. Right, so he carried out a flame test and the color was crimson. Okay, well, which one was it? Barium is green, calcium is a brick red, lithium, well, that is fairly, most people say it's scarlet, but that's not an M2 plus ion because that's Li1 plus because it's group 1. And strontium does give you a crimson, so strontium is the most likely identity there. Okay, now, so we're saying now in this bit here that it is not nickel carbonate. It's not nickel carbonate. It's not nickel, the metal. It is actually strontium. So it's strontium chloride is the product, and strontium carbonate was the initial stuff you started off with. So calculate the percentage yield if that was the case. Okay. So what we need to remember here is the equation again. So this time we got, well, it's strontium carbonate reacting with 2 moles of hydrochloric acid to form SrCl2 and CO2 and water. And then this, of course, is going to crystallize out to give us SrCl2.6H2O. Right, don't forget, we had this was in excess, the metal carbonate was in excess, and so we need to work out the moles of HCl, which we've done already. So the moles of HCl is equal to the concentration times by the volume. Now we added, the concentration was 0.8, and we added 150 centimeters cubed of that to the carbonate. That was the limiting reagent. That gave us 0.12 moles. How many moles of strontium chloride would that give us? Well, it's a 2 moles to 1 mole ratio. So we're going to say the moles of Sr, or the hydrated crystals, if we get 100% yield, should be 0.06. So let's work out the mass of that if 100% yield, or the expected, is equal to the moles multiplied by the MR of the hydrated crystals. Now let's work that out. Strontium in your periodic table has got a mass of 87.6. So it's going to be 87.6 plus 2 times plus 2 times, where are we? Right, 2 times 35.5 for chlorine plus 6 times 18. That gives us an MR of 266.6. Okay, that's how many, that's the MR of that. So the expected mass of the strontium chloride hydrated is going to be 0.06 multiplied by the MR, 266.6. That gives us 15.99 grams. Okay, but what did we actually get? We didn't get 15.99 grams, we got 14.26 grams up there. Okay, so the percentage yield is the actual over the expected mass multiplied by 100. That's 14.26 divided by 15.99 times 100, which gives 89.1%. But it says here to give it to 2 significant figures, so we should remember to change that as a final answer to be 89%. And that is as far as I'm going to go with this paper in this video. I'm going to complete it in the next video.